When you look up at the night sky, truly look away from the city lights, what do you feel? You see a blanket of stars, so many it's impossible to count. It's beautiful and it's humbling. It makes you feel small, but it also makes you wonder. Across that ocean of light on worlds orbiting those distant suns, is anyone looking back? Is there another mind somewhere out there feeling the same awe and asking the same question? Are we alone? This is perhaps the most profound question we can ask. It touches on our science, our philosophy, and our deepest sense of meaning. For most of human history, this question was pure speculation, a topic for stories and dreams. But in the last century, we have started to drag it out of the realm of philosophy and into the realm of science. We have tried to find a way to take this enormous, overwhelming question and break it down into smaller, manageable pieces. The most famous attempt at this came in 1961 from an astronomer named Frank Drake. He was preparing for a meeting and he wanted a way to structure the conversation. What he created was not an answer, but a framework for thinking. We call it the Drake equation. It sounds intimidating, but it's really just a string of questions, a list of all the things we need to know to find the answer. It starts simple and gets harder. It looks something like this. First, you take the rate of star formation in our galaxy. How many new stars are born each year? Then you multiply that by the fraction of those stars that have planets. Then you multiply that by the number of planets in each of those systems that are in the habitable zone. Not too hot, not too cold, where liquid water could exist. Then the fraction of those good planets that actually develop life. Then the fraction of that life that evolves to become intelligent. Then the fraction of that intelligence that develops technology we could detect like radio signals. And finally, the last and most difficult variable, L. L stands for the length of time that a civilization remains detectable before it disappears. When Drake first wrote this down, almost every single one of these terms was a complete mystery. We had no idea if other stars had planets. For all we knew, our own solar system was a 1 in a billion fluke. We were guessing in the dark. But then everything changed. In the last 20 years, we have turned on the lights. Thanks to instruments like the Kepler Space Telescope, we have found planets. And we haven't just found a few, we've found thousands. Kepler worked by staring at a single patch of sky, monitoring over 150,000 stars and waiting. It was looking for a tiny rhythmic dip in a star's light, the telltale sign of a planet passing in front of it. What Kepler and other missions have told us is staggering. Planets are not rare, they are the rule. The data suggests that almost every star in our galaxy has planets. Not only that, but a huge portion of them are small rocky worlds like Earth. And many of those are in the habitable zone. Suddenly, one of the biggest unknowns in the Drake equation isn't unknown anymore. The universe, it seems, is a factory for worlds. There are billions, perhaps tens of billions of potentially Earth-like planets in our own Milky Way galaxy alone. This should be fantastic news, right? The galaxy must be teeming with life. And this is where the silence begins. This is where the big problem arises. This is the great contradiction, the core of the mystery. It's known as the Fermi paradox. In the 1950s, the brilliant physicist Enrico Fermi was at lunch with his colleagues. They were discussing this very topic, the high probability of alien life. And in the middle of the conversation, Fermi suddenly looked up and asked a simple, devastating question. Where is everybody? This is the paradox. The math tells us the galaxy should be full. The observations tell us it's empty. Let's break down why this is such a problem. Our galaxy, the Milky Way, is about 13.5 billion years old. Our solar system is only about 4.5 billion years old. That means there have been billions of years and billions of other star systems where life could have evolved long before us. If a civilization developed on the other side of the galaxy, say 50 million years ago, which is nothing in cosmic time, what would they do? They would explore. They would expand. Even with technology we can imagine today, like a ship that could travel at 1% of the speed of light, you could cross the entire 100,000 light-year-wide galaxy in about 10 million years. Again, 10 million years is a blink of an eye compared to the age of the galaxy. If even one civilization had done this, they would be everywhere. Their probes, their ships, their signals, or just the artifacts of their existence would be all over the galaxy. They should have been here in our solar system millions of years ago. But when we look, we see nothing. When we listen with our radio telescopes, we hear nothing. Just the hiss of empty space. This is the great silence. So how do we solve this? Where is everybody? The silence itself is a clue, and it forces us to confront some fascinating and in some cases terrifying possibilities. One idea is that one of the terms in the Drake equation is just incredibly fantastically small. Maybe life itself is the bottleneck. Maybe the jump from non-living chemicals to a living cell, a process called abiogenesis, is so rare that it only happened once here on Earth. Or maybe life is common, but intelligent life is the miracle. Maybe the galaxy is full of bacteria and algae, but a creature that can build a radio telescope is a unique event. This is the rare Earth hypothesis. We are simply the first or the only ones. Another darker possibility lies in that final variable L. What if intelligence is common, but the lifespan of a civilization is tragically short? What if every species that reaches our level of technological power, the power to harness the atom to alter the climate to create artificial intelligence, inevitably destroys itself? In this scenario, the sky is silent because civilizations don't last long enough to make the journey. They flicker into existence, broadcast signals for a few hundred years, and then go silent, snuffed out by their own inventions. We right now would be in the middle of passing this great filter, and we don't know if we'll make it. Of course there are other ideas. Maybe we're just looking for the wrong thing. We're scanning for radio waves because that's what we use. It's like trying to find a modern city by listening for the sound of drums. What if advanced civilizations use modulated neutrinos, or gravitational waves, or some other form of communication we can't even comprehend? The galaxy could be a bustling city of light and information, and we are simply deaf and blind to it. There's also the zoo hypothesis. This is the idea that they are here and they are watching us, but they have decided not to interfere. They are observing us like we observe animals in a nature preserve or a zoo. They have a strict prime directive of non-interference waiting for us to reach a certain level of maturity. And finally, there is the most humbling possibility that we are fundamentally misunderstanding what life is. We are looking for carbon-based water-dependent creatures who live on rocky planets because that's what we are. What if the most common form of intelligence in the universe is a vast planet-sized mind, or a digital consciousness living in the plasma of a star? We might be looking right at it and not even have the framework to recognize it as alive. A rare Earth, a deadly filter, a hidden world, or a profound failure of our own imagination. The silence of the universe is not an answer. It is a question. And to even begin to find an answer, we must first understand the one data point we have, the one place in the entire cosmos we know life exists. We have to look back at ourselves. We have to tell the story of our own home. For the longest time when we looked up at the night sky, we were asking a question, almost in the abstract, are we alone? We studied our own solar system, probing Mars, dreaming of the moons of Jupiter and Saturn, because that was the only neighbourhood we knew. We had our 8 or 9 planets, a few dozen moons, and a vast empty darkness between the stars. The stars themselves were just points of light, beautiful but solitary. We wondered if they too had families of planets, but it was pure speculation. It was a question for philosophy, for science fiction. Then in the 90s, everything changed. Philosophy became observation. The abstract question became a practical scientific hunt. We found the first planets orbiting stars other than our Sun. We call them exoplanets. This discovery triggered a revolution in thought that we are still living through. It's a quiet revolution happening in datasets and telescopic light curves, but its implications are louder than an earthquake. The points of light in our sky are not solitary. They are by and large an invitation. They are solar systems. The immediate question, the one that drives us, is which of them could be like Earth? Which of them could be a home? This led to one of the most beautiful concepts in astronomy, the habitable zone. We often call it the Goldilocks zone. It's a wonderfully simple idea. Not too hot, not too cold. It's the region around any given star where the temperature is just right for liquid water to exist on the surface of a planet. Why liquid water? Because as we discussed, life as we know it is a symphony of chemistry that takes place in a liquid solvent, and water is the best solvent we can imagine. It's stable, it's abundant, and it facilitates the complex dance of molecules. If a planet is too close to its star, any water would boil away into space. If it's too far, it would freeze into a world of solid ice. The habitable zone is that perfect temperate orbit where a planet can have oceans, lakes, and rivers. For decades, this Goldilocks zone was a theoretical band of empty space we drew on diagrams. We didn't know if planets even formed there. Maybe planets were rare. Maybe rocky planets were rare. Maybe our solar system with Earth sitting perfectly in this life-friendly region was a 1 in a trillion cosmic lottery ticket. And then in 2009 we launched a telescope with a singular purpose to stare at one patch of the sky and find out. Its name was Kepler. The Kepler Space Telescope was a game changer. It wasn't designed to take beautiful detailed pictures of these planets. It couldn't. They're impossibly small and faint, completely washed out by the glare of their parent stars. Instead, Kepler used a brilliantly simple and patient method called the transit method. It stared unblinking at a field of over 150,000 stars. It just watched. It was looking for a tiny, almost imperceptible dimming of a star's light, a dimming that happens when a planet from our point of view passes in front of its star. It's like detecting a gnat flying in front of a searchlight miles away. Kepler watched and it waited, and the data began to pour in. What Kepler found fundamentally rewrote our understanding of the galaxy. It found not just a few planets, but thousands. It found them around big stars and small stars. It found giant planets, and most importantly, it found small rocky Earth-sized planets. And here is the most profound discovery: it found that planets like ours are not rare. They are common, unbelievably common. The data suggests that on average, there is at least one planet for every star in the sky. Think about that. The next time you look up at the Milky Way, that band of light containing hundreds of billions of stars, you're looking at a galaxy of planets. Kepler told us that small rocky worlds in the Goldilocks zone are everywhere. The universe, it turns out, is practically overflowing with a real estate category we might call potential Earths. This was a staggering realization. The lottery ticket we thought we were holding was, it seems, given out to almost everyone. The galaxy is full of stages. The question is anyone performing on them? Kepler could find the stages, but it couldn't see the actors. It told us that a planet was there, its size, and how close it orbited its star. It couldn't tell us what the planet was like. Does it have an atmosphere? Does it have water? Does it have clouds? That is the next chapter. That is the job of the new generation led by the incredible James Webb Space Telescope. If Kepler was the census taker finding the houses, Webb is the detective peering through the windows. Webb is designed not just to find planets, but to analyze them. It uses a technique we call spectroscopy. When a planet transits its star, a tiny fraction of the starlight passes through the planet's atmosphere if it has one. On its way to Webb's mirrors, that light gets filtered by the chemicals in that atmosphere. Different molecules like water vapor or carbon dioxide or methane absorb very specific colors or wavelengths of light. Webb is so sensitive that it can catch that filtered light and spread it into a rainbow spectrum. And in that spectrum, it can see the dark barcodes left by the molecules in the alien sky. We are right now at the very beginning of this. We are just starting to analyze the air of worlds orbiting other stars. We are looking for what we call biosignatures, signs of life. We are looking for the chemical fingerprints of a living world. Perhaps an atmosphere rich in oxygen, a gas that is so reactive it shouldn't exist in large amounts unless something like plants on Earth is constantly replenishing it. Or perhaps a strange mix of gases like methane and oxygen together that are in such chemical imbalance they strongly hint that a biological process is at work. Kepler showed us the targets. Webb is taking the shot. We have moved from "are there other worlds" to "which of these worlds is alive?" And the worlds we've found, they defy imagination. They have shown us that our solar system is perhaps not the template, but just one possible variation. We have found super-Earths. These are planets larger than Earth, but smaller than Neptune. They are the most common type of planet Kepler found, and yet we don't have a single one in our own solar system. Are they giant rocky planets with crushing gravity? Or are they mini Neptune's worlds with no surface at all, just a dense atmosphere over a core of ice and rock? We have found ocean worlds, planets that modelling suggests could be covered in a single global ocean hundreds of kilometres deep, worlds where the very concept of a continent doesn't exist. We've found one of the most fascinating possibilities: planets tidally locked to their stars. Most planets in the habitable zones of small, cool red dwarf stars, the most common stars in the galaxy, will be like this. Just as our moon always shows the same face to Earth, these planets always show the same face to their sun. This creates a world of permanent extreme contrasts. One side is locked in eternal scorching daylight, the other is frozen in an endless, unimaginable night. But in between, in the Terminator zone, a thin ring of perpetual twilight that circles the globe, the temperature could be just right. Life could exist in an endless sunset with howling winds circulating heat from the day side to the night side. And then there are the truly strange worlds. Planets so close to their stars that their surfaces are molten oceans of lava. Puffy planets, giants the size of Jupiter, but with the density of styrofoam, their atmospheres bloated by intense heat. We've even found pitch-black planets, dark as asphalt, that absorb almost all the light that falls on them. The exoplanet revolution has done something profound to our perspective. Before Earth felt singular. A unique blue marble, a precious and solitary miracle. What we are learning is that Earth is likely not a miracle but a process. It is not a single rare object. It is part of a vast, continuous spectrum of worlds. The universe is a factory for planets, and it is endlessly creative. It makes lava worlds, gas giants, ocean worlds, and worlds of rock and ice. And somewhere in that vast creative diversity, it makes worlds like ours. The discovery of exoplanets has not made Earth less precious. On the contrary, it has contextualized our preciousness. We are not a lonely outpost. We are perhaps one part of a galactic neighborhood, a living example of a potential that exists in billions of other places. The search is no longer for a single point of light. The search is for our neighbors. So we've found these special places in the cosmos, these just right worlds in the habitable zone. We've pointed our telescopes at a distant, watery-looking planet. But what are we actually looking for? We can't see cities. We can't see forests. From dozens of light years away, a planet is just a single point of light, a tiny pixel. We are not looking for sights. We are looking for smells. We are hunting for the chemical fingerprints of life. We are searching for a planet's breath. These fingerprints are called biosignatures. A biosignature is any chemical gas or trace that suggests the presence of biology. On Earth, our air is a powerful biosignature. Think about it. Our atmosphere is about 21% free oxygen. Oxygen is a violently reactive gas. It loves to grab onto other things, it rusts metal, it fuels fires. If you just left a cloud of oxygen by itself, it would quickly bind with rocks and minerals and disappear from the air. The only reason our sky is full of oxygen is because for billions of years plants and tiny microbes have been constantly making more. They breathe in carbon dioxide and they breathe out oxygen. Without life, our atmosphere would be radically different. So oxygen is a top-tier biosignature. Methane is another. Yes, volcanoes can release methane, but on Earth a huge amount of methane is produced by life from microbes in swamps to cows. And then there's ozone. Ozone is just 3 oxygen atoms stuck together, and it's created when sunlight zaps regular oxygen. Finding ozone is an indirect but strong hint that you first have a lot of oxygen. How on earth do we smell these gases from trillions of miles away? We use a beautiful technique called spectroscopy. The simplest way to think about it is this: we are reading a planet's barcode. When a planet passes in front of its star, a tiny, tiny fraction of the starlight shines through the planet's atmosphere on its way to us. Different gases in that atmosphere absorb different, very specific colors of light. If we take that starlight and spread it out into a full rainbow spectrum, we won't see a smooth, perfect rainbow. We will see black lines missing like the black bars in a supermarket barcode. Water vapor absorbs certain colors. Methane absorbs other colors. Oxygen absorbs different colors still. Each chemical has a unique, unforgeable barcode. By looking at which colors are missing from the starlight, we can read the ingredients list of a distant planet's air. And we are already doing this. The James Webb Space Telescope is right now reading the barcodes of exoplanets. One of the most tantalizing hints came from a planet called K2-18b. It's a Hycean world, a name for a planet that might have a deep water ocean under a thick hydrogen-rich atmosphere. The telescope found methane and carbon dioxide, which is fascinating, but it also found a hint of something else, a molecule called dimethyl sulfide, or DMS. Now, this is not confirmed, it is a weak signal and could be a mistake, but if it is real, it is world-changing. Why? Because on Earth, DMS is only produced by life. There is no known geological process that makes it in large amounts. It is a waste product from marine plankton. Finding DMS on K2-18b would be the closest thing we have ever had to a direct sign of a living process on another world. But the real holy grail of biosignatures isn't just one gas, it's finding 2 gases that have no business being in the same room. This is the core concept chemical disequilibrium. It means an atmosphere that is not in balance. Think of it this way. If you lock a cat and a mouse in a small box, what happens? Very quickly you will be left with just a cat. The system finds its equilibrium, its stable, balanced state. A planet's atmosphere is the same. Methane, the mouse, and oxygen, the cat, destroy each other when they are together. They react and turn into water and carbon dioxide. If you find a planet's atmosphere that is full of both oxygen and methane at the same time, it is like looking in the box and seeing the cat and the mouse just sitting there. It means something must be constantly refilling the box, something making new mice and something making new cats. That something is life. Earth's atmosphere is in a constant state of chemical imbalance maintained by the constant activity of biology. We're looking for a planet that feels chemically wrong, a planet that is being actively managed by life. But this is incredibly hard and we must be cautious. The universe is clever and can fool us. We worry about false positives. This is when a non-living process mimics a sign of life. For example, you could get a planet full of oxygen with no life at all. If a planet is very hot and wet and getting blasted by intense ultraviolet light from its star, that light could split water molecules H2O into hydrogen and oxygen. The superlight hydrogen would float away into space, leaving the heavy oxygen behind. You'd see the oxygen barcode and celebrate all while the planet is totally sterile. Methane can be made by geological chemistry deep underground. We also have to worry about false negatives. This is when life is there, but we can't see it. What if the most interesting life in the galaxy isn't on the surface? What if it's hidden deep beneath a thick crust of ice, thriving in a warm, dark ocean clustered around volcanic vents? That's what we suspect for Jupiter's moon, Europa, and Saturn's moon Enceladus. That entire biosphere could live and die creating complex ecosystems, and we would never see a trace of it in the wisp of atmosphere if any high above the ice. Or what if the life is simply early? For the first 2 billion years of life on Earth, our atmosphere had almost no oxygen. Life was here, but it was just microbes. If an alien civilization had scanned our planet back then, they might have seen methane, but they could have easily dismissed it as interesting geology and moved on, missing the greatest story in the solar system. So we have to broaden our search. We look for other things. We look for strange combinations of sulfur gases or ammonia. We even look for things like chloromethane. This gas is made by some ocean organisms on Earth, but it's also an industrial chemical we create. This blurs the line between a biosignature, a sign of life, and a technosignature, a sign of civilization. The hunt for biosignatures is a patient, careful science. It's a search for imbalance. We are looking for a world that isn't quiet, a world that isn't settled. We are looking for a planet that across all the silent, sterile light years is breathing. When we look for life in the cosmos, we are trapped by the one example we have. We are life. We are the template. And so when we design our probes, when we aim our telescopes, we are almost always looking for ourselves. We look for planets that look like a young Earth. We look for water just like the water that fills our oceans. We look for carbon, the element that forms the backbone of every single molecule inside of us. This is what scientists call carbon chauvinism. It's the assumption, perhaps arrogant, that because carbon is so good at creating life here, it must be the only thing that can create life anywhere. To be fair, carbon is magnificent. It is the universe's ultimate building block. An atom of carbon has 4 connection points, 4 hands reaching out ready to link up with other atoms. It can form long, complex, stable chains. It can build rings. It can create the intricate architecture of proteins and the spiraling ladder of DNA deoxyribonucleic acid. It is stable, it is abundant, it is versatile. It is the perfect scaffolding for complexity. But is it the only one? Is the universe really that limited in its imagination? Or is it our imagination that is limited? When we look at the periodic table of elements, we see other possibilities. The most famous, the one that science fiction has loved for 100 years, is sitting right below carbon on the chart: silicon. Silicon shares carbon's greatest strength. It also has 4 hands. It can also form 4 bonds. It seems like the perfect understudy ready to take carbon's place in a different kind of biological play. You can imagine a creature not of soft flesh, but of living crystal. A being that is part rock, part life. But when we look closer, the problems start. Silicon atoms can form chains much like carbon does, but those bonds are weaker. They are more fragile, more easily broken by radiation or other chemicals. Worse, silicon has an overwhelming, almost self-destructive affinity for one particular element, oxygen. When carbon combines with oxygen, it creates carbon dioxide. This is a gas. It's a brilliant waste disposal system for life on Earth. We breathe in oxygen, we burn our carbon-based fuel, and we exhale the waste product carbon dioxide gas, which then floats away. It's efficient. When silicon combines with oxygen, it creates silicon dioxide. We know this substance, we are surrounded by it. It is sand, it is quartz, it is for all practical purposes rock. Now imagine a silicon-based organism. It tries to breathe, it takes in energy, it processes its silicon-based fuel, and its waste product is sand, solid rock. How does a creature exhale sand? How does it get rid of its own waste if that waste is a solid crystal that builds up inside of it? It's a fundamental and perhaps fatal plumbing problem. There's another issue. The complex silicon molecules that would be needed for life, the ones that would have to store information like DNA, are highly unstable in water. Water, the very thing we consider essential for our life, would be a deadly poison to a silicon-based biochemistry. It would dissolve them, break them apart. So if silicon life exists, it must be in a place that is profoundly alien to us. It would have to be a place with almost no water, and it would need a way to solve the problem of exhaling solid rock. It's not impossible, but it's difficult. This brings us to our second and perhaps even deeper bias, our water chauvinism. Life on Earth is fundamentally a water-based chemistry. Water is our universal solvent. It's liquid across a wonderful range of temperatures. It's a polar molecule, meaning it has a slight positive charge on one end and a slight negative on the other, which makes it incredibly good at dissolving salts and other chemicals moving them around a cell. And in a strange and vital quirk, it floats when it freezes. Ice forms on top of a lake, insulating the liquid water below, allowing life to survive the winter. Water is amazing, but is it the only liquid that can host life? Let's journey out far from the sun to the cold, hazy realm of Saturn. Let's visit its largest moon, Titan. Titan is a world of wonders. It is larger than our planet Mercury. It has a thick, soupy orange atmosphere, thicker than Earth's, made mostly of nitrogen and methane. We sent a probe there called Huygens, which parachuted through those clouds and landed on the surface. It sent back photographs. Those photographs showed coastlines. They showed riverbeds. They showed great dark seas. Titan is the only other place in our solar system that we know of with stable liquid on its surface. But it is not water. The temperature on Titan is incredibly cold, hundreds of degrees below zero. At that temperature, water is not a liquid, it is a rock. The ice on Titan is as hard as granite. The bedrock of Titan is water. The liquid that flows in its rivers and fills its lakes is liquid methane and ethane. These are chemicals we know as natural gas on Earth. On frigid Titan, they are liquid. It rains methane. Could life exist there? Could something be swimming in those ethane seas? If it does, it is life as we absolutely do not know it. It would be a life that considers water a rock and oxygen a poison. Its cells could not be made of the fatty lipids that make up our own. Those would dissolve instantly. Scientists have theorized that life on Titan might build its cells from azotosomes molecules based on nitrogen that could form a stable, flexible bubble in liquid methane. Its entire metabolism would be different. It wouldn't burn oxygen. Instead, it might breathe in hydrogen gas and eat a chemical called acetylene, and its waste product, methane, the very liquid it swims in. But there is another, more profound difference. Heat is energy. It is motion. It is the engine of chemistry. Life on Earth is fast because our planet is warm. Reactions in our cells happen in microseconds. On Titan, it is desperately cold. The chemical reactions, the very processes of life, would be agonizingly slow. A creature on Titan might take a breath only once an hour. Its heart might beat once a decade. A single thought traveling through a network of alien nerves might take 1,000 years to complete. It would be a life lived on a completely different timescale. We could land a probe right next to one of these creatures and we would see nothing, just a strange frozen plastic-like object. We would analyze it and declare it dead because we are too fast. We are like hummingbirds trying to understand a glacier. We operate in different worlds on different clocks. We would not even recognize it as life. And methane is not the only alternative. What about ammonia? Ammonia is a liquid at colder temperatures than water, and it's also a pretty good solvent. What about sulfuric acid? The clouds of Venus are full of it. It's hostile to us, but who is to say that life couldn't find a way to use it as its solvent? This all forces us to confront the biggest, most difficult question. We are looking for life. But what is life anyway? We have a checklist, one that NASA often uses. Does it have a metabolism? Does it eat and process energy? Does it reproduce? Does it make copies of itself? Does it evolve? Does it change over generations to adapt to its environment? This definition works perfectly for every living thing on Earth, from a bacterium to a blue whale. But is it the only definition? Think about a crystal. A crystal grows. It takes material from its environment like salt in water and arranges it into a complex, ordered pattern. It reproduces when a piece breaks off and seeds a new crystal. But we all agree a crystal is not alive. Think about a fir. A fir eats fuel wood, it breathes oxygen, it grows, it reproduces by sending out sparks that start new fires. But fire is definitely not alive. The line begins to blur. Some scientists have proposed a more general, more philosophical definition. They say that life is just a process. It is any system that locally fights against the universe's slide into chaos. The universe has a fundamental rule, the second law of thermodynamics. It says that everything over time tends to fall apart. It moves from order to disorder. Entropy always increases. A hot cup of coffee always cools down. A new car always rusts. A star always burns out. Life is the one thing that defies this, at least for a little while, in a small place. Life is a system that takes in disordered energy like raw sunlight and simple chemicals and builds complexity. It builds order, it builds a leaf, it builds a brain, it builds a civilization. Life is the universe's way of organizing itself. It is the universe becoming aware of itself. If that is our definition, then life could be anywhere in any form. It could be a vast, slow-thinking cloud of plasma in interstellar space. It could be a complex pattern of self-replicating chemical reactions in the soupy atmosphere of Jupiter. It could be a digital being born inside a machine. We are just one form, a carbon and water form of this universal tendency toward complexity. So if we can't look for carbon and we can't look for water, how do we find that? How do we find something we can't even define? We have to look for the evidence of life, not life itself. We have to look for its footprint. We have to look for complexity. One way to do this is with machine learning. We can point our new telescopes like the James Webb Space Telescope at the atmosphere of a distant planet. We can gather all the data, all the light, and feed it to a powerful artificial intelligence. We don't tell the AI what to look for. We don't say find oxygen or find methane. We just say find the weird part. We ask it to find a signal that doesn't make sense, a pattern that shouldn't be there, because life, whatever it is, messes with its environment. It is noisy. It creates things that geology alone would not. On Earth, life created an atmosphere full of oxygen, a highly reactive, unstable gas. That much free oxygen just sitting there is a massive chemical improbability. It shouldn't exist. The only reason it does is because plants and algae are constantly relentlessly pumping it out. Our oxygen-rich air is a global biosignature. An alien astronomer looking at our solar system would see that oxygen in our atmosphere and know that something strange and wonderful is happening on the third planet. We are looking for that something elsewhere. A strange, complex mix of gases that has no business existing together. That will be the signal. That will be the sign of life. There is one other, more subtle sign we can look for. It's a beautiful concept called chirality. It's a Greek word meaning handedness. Look at your two hands. They are identical in their parts, but they are mirror images. You cannot place your left hand perfectly on top of your right hand. They are handed. Many of the molecules of life are the same way. Amino acids, the building blocks of proteins, can exist in two forms, a left-handed version and a right-handed version. Chemically, they are identical. If you were in a lab and you created amino acids by mixing simple chemicals, you would get a perfect 50-50 mix of left-handed and right-handed versions. It's random. It's chaos. But in life on Earth, it is not random. Every single amino acid used in every single protein in your body is left-handed. And the sugars like the ones that make up the backbone of your DNA are all right-handed. Life at its very beginning, for some reason we still don't understand, chose a side. Maybe it was a complete cosmic accident. A single molecule that happened to be left-handed was the first one to replicate, and it locked in that standard for all life that followed. This gives us an astonishingly powerful tool. If we send a probe to Mars or to the oceans of Europa, and we scoop up a sample of the soil or the water, we can check its handedness. If we find a random 50-50 mix of left and right-handed molecules, we will know it was just geology, non-living chemistry. But if we find a sample where all the amino acids are left-handed, or just as excitingly where they are all right-handed, that is the stamp of biology. That is a signal. That is the proof that a second independent genesis of life occurred separate from our own. It would be perhaps the single greatest discovery in the history of science. All of this leads to a final, profound and deeply unsettling thought. The famous question the Fermi paradox asks, where is everybody? We look up at the silent stars and we feel alone. But maybe the universe is not silent. Maybe it is shouting with life. Maybe it is everywhere in forms so alien, so slow or so fast that we are completely blind to it. The most terrifying possibility is not that we are alone. It is that we are not, and we are just not smart enough to see it. What if the Viking landers on Mars in the 1970s did in fact find life? Their experiments returned strange, ambiguous results that we are still debating today. We dismissed them. What if we were wrong? What if the complex, unexplained chemical signals in the atmosphere of Venus, or the strange methane cycles on Titan, are not geology? What if they are the breath of a global biosphere that we dismiss as noise? The greatest challenge in the search for life, then, is not in building bigger telescopes or faster rockets. The greatest challenge is in our own minds. It is in overcoming our own biases. We are trying to imagine the unimaginable. We are looking for something that we cannot define, and we must be prepared for the answer to be something that we do not understand. The search for alien life is in the end a search for the true limits of our own imagination. When we last spoke, we were staring into the great silence, wondering where everybody is. The Fermi paradox left us with a chilling question. Are we alone? Perhaps the problem isn't in the stars, but in ourselves. Perhaps we are looking for the wrong thing. We have spent so long looking for a mirror for a comfortable green and blue world just like ours, that we have been blind to the sheer stubborn, impossible creativity of life itself. Before we look out, let's look down into the places on our own world that we once considered sterile. Let's look at the dark, boiling, crushed, irradiated corners of Earth. We will find that our definition of home is tragically limited. We have a name for the creatures that live in these places. We call them extremophiles, the lovers of the extreme. And they are not just surviving in these environments, they are thriving. They are teaching us that our rules for life are merely suggestions. The first rule we had to break was the most fundamental, that all life on Earth depends on the sun. This was our dogma. The sun's energy captured by plants through photosynthesis forms the base of the entire food chain. Take away the sun and life ends. Then in 1977 we sent a deep-sea submersible to a place where the sun has never ever shined. Miles down at the bottom of the Pacific we found volcanic vents on the seafloor. We called them black smokers. These are chimneys gushing water from deep within the Earth's crust. This water is superheated to over 300 degrees Celsius. It is utterly black. The pressure is crushing, and it is loaded with chemicals that are pure poison to us like hydrogen sulfide. By all of our rules, this place should have been a sterile chemical desert. Instead, we found an oasis. It was teeming with life. Giant tube worms 6 feet long with no mouths and no stomachs coloured a brilliant fleshy red. Fields of mussels and clams. Ghostly white crabs crawling over each other in the darkness. The question was, what were they eating? They were eating the volcano. The bacteria at the bottom of this food chain were not using sunlight. They were using the chemicals and the heat from the vent itself. They were taking that poisonous hydrogen sulfide and through a process we call chemosynthesis turning it into energy. The larger animals then either ate the bacteria or in the case of the tube worms hosted them inside their bodies as permanent partners. This discovery changed everything. It meant that life does not need sunlight. It doesn't even need a surface. It just needs a source of chemical energy and a gradient of difference. Here the difference between the superheated chemical-rich water from the vent and the cold dark ocean water around it. Life found a way to build a city in that tiny energetic margin. If life can do this on Earth, why not in the dark liquid oceans we suspect are hiding beneath the icy crust of Jupiter's moon, Europa, or Saturn's moon Enceladus? They too have internal heat and chemical gradients. The black smokers of Earth gave us the first real tangible hope for life on those worlds. And that was just the beginning. Let's talk about temperature. We are incredibly fragile. A change of just a few degrees in our body temperature and we are in serious trouble. We like our world to be in that gentle liquid water range. Go to the hot springs of Yellowstone National Park. You see those brilliant yellow, orange and blue colours in the pools. That's not rock. It's microbes. These are thermophiles, the heat lovers. They thrive in water that is near boiling. But we've found others that go even further. We have found microbes living in the walls of deep-sea vents at 121 degrees Celsius. That is well above the boiling point of water at sea level pressure. They are not just surviving, they are reproducing, they are happy. Let's go to the other extreme, the Arctic and Antarctic ice sheets. For a long time we thought of ice as a sterile tomb. It is not. Drill deep into the ancient ice of Antarctica, and you will find cryophiles, the cold lovers. They live in tiny thread-like veins of liquid water that exist between the ice crystals. This water is incredibly salty, which keeps it from freezing at temperatures well below 0 degrees Celsius. These microbes have developed their own biological antifreeze to keep their internal machinery from turning to ice. Their metabolism is painfully slow. A single generation might take hundreds or even thousands of years, but they are alive. They are waiting. So a planet being too hot or too cold suddenly became a very relative term. What about chemistry? We like our water pure. We like our environment neutral. There are bacteria called acidophiles that live in places with an acidity that would dissolve metal. They thrive in environments 1,000,000 times more acidic than our own blood, some in conditions equivalent to pure battery acid. There are halophiles, the salt lovers, that live in places like the Dead Sea or the Great Salt Lake. The water there is so saturated with salt that it would pull all the moisture out of a normal cell, killing it instantly. To these microbes, it's home. They've found a way to balance their internal chemistry against this extreme. This brings me to my absolute favourite example, a true superhero of the microbial world. It's a bacterium called Deinococcus radiodurans. Its nickname is Conan the bacterium. This microbe's specialty is radiation. Space is filled with cosmic rays and solar radiation, which is deadly to most life. Radiation works by shredding DNA. It shatters the blueprint. For us, a dose of about 10 grays of radiation is lethal. Deinococcus can take 5,000 grays. When it gets hit with this level of radiation, its DNA, its genetic code, is literally shattered into hundreds of broken pieces. It should be dead, but for this microbe, it's just an inconvenience. It has an amazing ability. It has multiple copies of its genome. After the blast, it calmly and methodically starts pulling the broken pieces back into its cell. It has a complex, beautiful set of enzymes, a biological repair kit that recognizes the broken strands and piece by piece stitches its entire genome back together perfectly. In just a few hours, it is fully repaired, good as new and ready to divide. This little creature showed us that even the vacuum of space, even the unfiltered radiation of a star, is not necessarily a barrier to life. Life can and did evolve its own radiation shielding. We thought life was a thin, fragile layer on the surface of our planet. We were wrong. We've now found life inside rocks. In the cold, dry deserts of Antarctica, which look more like Mars than Earth, there is almost no visible life. But if you crack open a rock, you will see a thin coloured line just a few millimetres under the surface. These are endoliths, which means within rock. The rock is their home. It shields them from the harsh ultraviolet light and the dry winds. It traps tiny amounts of moisture. The rock itself is just translucent enough to let in a tiny bit of sunlight so they can photosynthesize. They live perhaps the slowest lives on Earth, but they are alive. When we look at the rocks on Mars, we are no longer just looking at rocks. We are looking at potential apartments. But the most profound discovery came from deep in the Earth. Miles down, in the deep gold mines of South Africa, 3 kilometers beneath the surface, we found life. This life has zero connection to our world. It receives no sunlight. It doesn't use chemicals from volcanic vents. It is trapped in rock in water that hasn't seen the surface in millions of years. So what does it eat? It eats the rock itself. More specifically, it is powered by radioactivity. The natural low-level radiation from the uranium and thorium in the rock splits water molecules into hydrogen and other components. The microbes eat this hydrogen. This is life completely independent of the sun. It is a biological system running on nuclear power. This means that any planet, even a rogue planet thrown out of its solar system wandering in the cold, dark emptiness of interstellar space, could still host life deep underground, powered by the heat and radiation of its own core. So, what is the lesson? What do these tiny, tough survivors tell us? They tell us to check our assumptions. They tell us to look in the margins. Let's take Venus. Venus is Earth's twin. It's about the same size, but it's a nightmare. The surface is over 450 degrees Celsius, hot enough to melt lead. The atmospheric pressure is 90 times that of Earth, enough to crush a submarine. It's hell, but the extremophiles tell us to look again. What about not the surface? What about high up, about 50 kilometers up in the atmosphere? Up there, the temperature is quite pleasant, maybe 30 degrees Celsius. The pressure is the same as on Earth's surface. There is a catch. The clouds there are made of concentrated sulfuric acid. Years ago, we would have laughed. Impossible! Now we think of the acidophiles on Earth thriving in battery acid, and we wonder, what if there is a form of life that spends its entire existence floating in those acidic but temperate Venusian clouds? It's a hypothesis, but it is a hypothesis born entirely from what the extremophiles have taught us. This is the great shift in perspective. We have been searching for comfort. We've been looking for places that are habitable, which we defined as comfortable for us. But life doesn't need comfort. Life needs energy. That's it. Life is a process. It is a clever system for exploiting a gradient, a difference, the difference between a hot vent and cold water, the difference between a chemical-rich rock and the water around it, the difference between a high-energy state and a low-energy state. Life is the engine that positions itself in that flow and siphons off a little bit of that energy to make copies of itself. The habitable zone is not just a narrow, gentle band of orbits around a star. Habitable zone is anywhere there is a source of energy to be used. It is in the icy dark oceans of Europa. It is in the hydrocarbon lakes of Titan. It is in the acidic clouds of Venus. It is deep in the rocks of Mars. Earth has shown us that life's tenacity is limited only by its imagination. And its imagination is far, far greater than ours. We have been searching for so long, looking out into the deep, deep black. We've scanned distant stars for the faint dip in light that signals a passing planet. We've listened with our great radio telescopes for a whisper, a pattern, a signal that we are not alone. And in that search, we've held on to one main idea, one guiding principle, the Goldilocks zone. We believed for decades that life needed a very specific set of circumstances. It needed a planet like Earth, rocky and solid. It needed to be not too hot and not too cold. It had to be at that perfect, just right distance from its star so that liquid water could exist on its surface. We were looking for Earth's twin, a pale blue dot orbiting a sun just like ours. This idea makes perfect sense. It's based on the only example of life we have, us. We are creatures of the sun. Every bite of food you've ever eaten, every breath of air you've taken can trace its energy right back to that burning star in the sky. But what if that assumption, that logical, sensible idea is holding us back? What if sunlight is just one way to power life and not the only way? What if the Goldilocks zone is far, far larger than we ever imagined, and includes places we always dismissed as frozen dead and impossible? The most revolutionary discoveries about life might not come from a distant star system. They might be waiting for us right here in our own solar system. Not on the sun-baked familiar planets, but in the cold, dark outer reaches in places that are by all traditional definitions uninhabitable. We are going to shift our focus from the fire of stars to the power of gravity. We are going to look at the moons orbiting the giants Jupiter and Saturn, and we are going to find oceans. The reason these places are not frozen solid is a beautiful bit of physics called tidal heating. It's the same force that causes the tides in our oceans, but magnified to an incredible degree. Imagine you have a small, cold rubber ball in your hand. If you just let it sit, it stays cold. But if you start to squeeze it and relax, squeeze and relax over and over again, thousands and thousands of times, what happens? The ball warms up. Hippo. The friction from all that stretching and compressing generates heat from the inside out. Now imagine that rubber ball is a moon, and the hand squeezing it is the colossal gravity of a planet like Jupiter. As the moon orbits, it's not in a perfect smooth circle. Other moons pull on it, nudging it closer to Jupiter, then farther away. With every orbit, it gets stretched and squeezed, flexed like a piece of putty. The rock and ice in its core and mantle rub against each other, generating immense constant friction. This gravitational kneading, this tidal heating is an engine. It's an internal furnace that doesn't need a single ray of sunlight. It generates enough warmth to do the impossible, to melt ice in the frozen darkness of space. Our first stop is Jupiter and its fourth largest moon, Europa. From a distance, Europa looks like a smooth white billiard ball, but cracked. Its entire surface is a shell of water ice crisscrossed by a fantastic chaotic network of reddish-brown lines and ridges. It looks like a frozen lake on Earth in the middle of spring where the ice has broken apart and refrozen over and over. For decades, scientists looked at these crags and wondered, this terrain, this chaotic terrain as it's called, looks like places on Earth where massive glaciers or ice shelves have broken apart, churned up and then frozen back into place. This suggests the ice shell isn't static, it's floating, it's moving. But floating on what? The real proof came from the Galileo spacecraft which orbited Jupiter in the 1990s. As it flew past Europa, it measured the moon's magnetic field. It found something strange. Europa didn't have its own magnetic field like Earth does. Instead, it had an induced magnetic field. This field was being created because Europa was moving through Jupiter's own massive magnetic field. This finding is profound. To create a magnetic field like that, you need a conductor, something that can carry an electrical current. Ice doesn't conduct electricity. Rock doesn't do it very well. But what does a large, deep body of salt water? The data was undeniable. The only way to explain Europa's magnetic signal was the presence of a global liquid ocean hidden beneath that shell of ice. Let that sink in. This isn't a small lake or a slushy puddle. We are talking about a global ocean covering the entire moon, estimated to be 60 to 100 miles deep. Think about our planet. The deepest part of Earth's ocean, the Mariana Trench, is about 7 miles deep. Europa's ocean is 10, maybe 15 times deeper. When you do the math, this one small moon, smaller than our own, likely contains 2 to 3 times more liquid water than all of planet Earth combined. All the oceans, all the rivers, all the lakes, all the glaciers on Earth. Take all that water, double it, and that's what is sloshing around inside Europa right now. So we have the first ingredient for life, liquid water. Vats of it. But life needs more. It needs energy and it needs food, the chemical building blocks. Europa has those too. The same tidal heating that melts the ice is also flexing the rocky seafloor below the ocean. This intense geological activity would almost certainly create hydrothermal vents. These are the same kinds of deep-sea chimneys we find on Earth's ocean floor, places like the Lost City. Here on Earth, in the total absence of sunlight, these vents are oases for life. They gush out hot mineral-rich water, creating a chemical feast for bacteria. These bacteria form the base of an entire food chain. Crabs, shrimp, and tube worms all thrive in this permanent darkness, powered not by the sun but by the chemical energy from the planet's core. Is it possible that at the bottom of Europa's dark global ocean, similar vents are pumping out heat and chemicals? Is it possible that life has taken root there completely independent of the sun? The answer seems to be a resounding maybe, and we may not even have to drill to find out. In recent years, the Hubble Space Telescope has captured hints of something astonishing: vast plumes of water vapor geysers erupting from Europa's surface. These plumes seem to shoot more than 100 miles into space before freezing and falling back down. If these plumes are real, they are samples of that hidden ocean delivered to us free of charge. We could just fly a spacecraft through them and taste the water. But Europa is not even our most dramatic candidate. For that, we have to travel to Saturn. We need to talk about a tiny moon called Enceladus. Enceladus is small. It's only about 300 miles across. You could fit it inside the state of Arizona. We always thought it was just a small, boring ball of ice, and we would have kept thinking that if not for the Cassini spacecraft. Cassini orbited Saturn for 13 years, and it completely rewrote our understanding of the outer solar system. In 2005, it flew past Enceladus and saw something that shocked the entire scientific community. From the moon's south pole, from a series of long parallel cracks nicknamed tiger stripes, giant plumes of water were erupting. These were not small tentative geysers. These were continuous massive jets of ice crystals, water vapor and other materials blasting hundreds of miles out into space with incredible force. Enceladus was actively spraying its own ocean into the void. This discovery was a game changer. Europa's ocean was inferred, Enceladus's ocean was advertising, and Cassini had the right tools for the job. It didn't just take pictures, it had instruments that could analyze the dust and gas it flew through. So mission controllers did something brave. They flew Cassini right through the plumes. They tasted the ocean of Enceladus. What they found has become one of the most important discoveries in the history of planetary science. First, they confirmed it was mostly water ice and vapor. No surprise there. Second, they found salt, sodium chloride table salt, Earthketor. This was a crucial piece of the puzzle. It meant the water wasn't just a pocket of melted ice. It was a true salty sea, just like our oceans. It proved the water was in direct contact with the moon's rocky core, dissolving minerals from it. Third, they found organic molecules. Not life itself, but the building blocks of life. They found methane, formaldehyde, acetylene, propane. These are the carbon-based compounds that form the basis of all life as we know it. The food was there, but it was the fourth discovery that provided the smoking gun. Cassini detected tiny microscopic grains of silica. Silicon dioxide. This is essentially fine sand. You may be thinking, sand, so what? But this specific kind of nanoparticle, this tiny grain of silica, is incredibly important. On Earth, these particles only form under a very specific set of conditions when water that is very hot, at least 90 degrees Celsius, or 194 degrees Fahrenheit, interacts with rock. This was the proof. This wasn't a theory or a model. This was a receipt. The silica grains being blasted into space from Enceladus were manufactured at the bottom of its ocean in active hot bubbling hydrothermal vents and then shot out through the ice in a geyser. This is not a maybe. This is not a could be. Enceladus has right now active hydrothermal vents. Think about what this means. This tiny frozen moon orbiting Saturn in the dark has every single ingredient for life as we know it. It has liquid water in a salty global ocean. It has energy both from tidal heating and from the hot chemical broth of the vents. It has the right chemistry, a rich soup of organic molecules. We have found in our own solar system a place that has the holy trinity for life. A place where if you were to drop a colony of Earth's deep-sea bacteria, they would probably be very, very happy. The only question is, has life already started there on its own? These two moons, Europa and Enceladus, have forced us to completely redefine what it means for a world to be habitable. The Goldilocks zone. The idea that you need to be close to a star was a good first guess, but it was based on our bias for surfaces and our bias for sunlight. Life, it seems, doesn't care about surfaces, it doesn't need sunlight, it just needs energy. And it can get that energy from gravity. It doesn't need a blue sky. It can thrive in a lightless ocean miles beneath a sheet of ice. This expands the habitable zone in a way we never thought possible. It's not just a thin band around a star. The new habitable zone is anywhere. Anywhere you have a source of energy and liquid water. Suddenly, the solar system is not a collection of 9 planets and a few dead rocks. It's a place of hidden vitality. Europa and Enceladus are just the most obvious candidates. Jupiter's moon Ganymede might have a club sandwich of water and ice layers. Saturn's moon Titan has an ocean of water under its oceans of methane. Even distant Triton orbiting Neptune shows signs of geysers. Even tiny faraway Pluto shows evidence of a possible subsurface ocean. Our solar system is not empty, it is full of oceans, and we are going back to check. The next great chapter in this search is already being built. NASA's Europa Clipper mission is scheduled to launch soon. It will be the most advanced probe we have ever sent to the outer solar system. It won't land, the radiation around Jupiter is too intense, but it will perform dozens of high-speed, low-altitude flybys of Europa. It will be equipped with ice-penetrating radar, an instrument that will map the ocean it cannot see. It will measure the thickness of the ice shell. It will hunt for active plumes, and if it finds them, it will fly through them with instruments 1,000 times more sensitive than Cassini's. It will in essence scan Europa for life. It will tell us if that ocean is not just watery but habitable. We began this journey by looking for a mirror of Earth, a comfortable sunlit world where we might find familiar forms of life. But the universe in its wisdom has pointed us in a different direction. It has shown us that the most likely places to find life are nothing like Earth at all. They are dark, they are cold, they are hidden. The greatest secret of the cosmos. The answer to that profound question, are we alone, might not be found by looking up at the shimmering stars. It might be found by looking inward at the quiet icy neighbours that have been hiding oceans of possibility right in our own backyard all along. We have spent our time together, looking out, looking back, and looking within. We've gazed at the impossibly large and the mind-bendingly small. We've imagined the spark of life emerging from warm ponds or ocean vents. We've felt the weight of the Fermi paradox, that profound question hanging in the cosmic air. Where is everybody? Perhaps the problem is that we have only been looking. What if instead we were to listen? This is the story of our attempt to do just that. It is the story of the search for extraterrestrial intelligence, or SETI. It is an endeavour born of pure distilled curiosity. It is the act of pointing a giant ear to the heavens and just listening. Listening for a whisper, a pattern, a single note in the cosmic static that says, we are here too. We are not just listening for life, we are listening for technology. A signal that could not have been made by a star, a planet, or a gas cloud. We are searching for a techno-signature. This could be a powerful focused beam of radio waves like a cosmic lighthouse, or it could be a pulse of laser light carefully patterned. It is the search for anything that when we find it makes us say that was not an accident. But before we ever thought to listen, we began to shout. Unintentionally, of course. For about 100 years, our planet has been wrapped in an expanding bubble of noise. Our first radio broadcast, our first television signals, our military radar, all of these have been leaking off the Earth, travelling outwards at the speed of light. This is our radio bubble. Right now, that bubble is just over 200 light years across. Every star inside that sphere has in theory been touched by our signals. A civilization 70 light years away might just be receiving broadcasts from the 1950s. They would be incredibly faint, like trying to hear a whisper from across an ocean. But the information is there, coasting through the void. It carries our music, our news, our wars, our commercials. It is our accidental introduction to the cosmos. In a very real way, we are a techno-signature. We are a source of artificial noise in an otherwise mostly natural symphony. The idea of listening on purpose is almost as old as radio itself, but it was an astronomer named Frank Drake who turned it into a real science. In 1960, he conducted Project Ozma. He pointed a large radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani. He was listening for a very specific kind of signal, a narrow-band signal. Think of it this way. The universe is naturally very noisy. A star or a galaxy broadcasts radio waves over a huge range of frequencies like a symphony orchestra playing every single note at once. It's a wall of sound, but an artificial signal like a radio station on your car stereo is narrow. It's packed into one tiny specific frequency. It's like a single clear flute note rising above the entire orchestra. That is what Frank Drake was listening for. He didn't find it, but he started something. He opened the door. So what are we listening for exactly? We are looking for the non-natural. We are looking for order. A signal that repeats with mathematical precision, a string of prime numbers, anything that betrays a mind and intention behind it. We have been confused before. In 1967, a graduate student named Jocelyn Bell Burnell detected a signal that was breathtakingly precise. It pulsed perfectly once every 1.3 seconds. For a thrilling, terrifying few weeks, the team wondered if they had found it. They nicknamed the signal LGM-1, which stood for Little Green Men. It turned out to be a pulsar, a rapidly spinning neutron star, a natural cosmic lighthouse. It was an amazing discovery, but it was not a message. This is the challenge. The universe is more clever, more strange than we can imagine. Nature can create patterns that look at first like intelligence. Our job is to be skeptical, to be thorough, and to keep listening for the one signal that cannot be explained away. And so far, after decades of listening with bigger and better radio telescopes, the result has been the same. Silence. A profound, echoing silence. This brings us to a great debate. If listening isn't working, should we try shouting on purpose? This is called active SETI, and we have done it a few times. In 1974, from the Arecibo radio telescope, we sent a powerful 3-minute message aimed at a star cluster called M13 over 25,000 light-years away. It was a picture drawn in the binary code of ones and zeros. It showed a stick figure, our DNA, our solar system. It was a message in a bottle thrown into the cosmic ocean. It won't arrive for 25,000 years, and any reply would take another 25,000. It was not a conversation, it was a statement. And of course there are other golden records placed aboard the 2 Voyager spacecraft now drifting in interstellar space. There are more complex greeting-carrying sounds and images of Earth, a best-of album for our planet. But the debate is fierce. Is this a good idea? Some scientists argue, what's the harm? We are already noisy. Shouting with intention is our best bet. If everyone is listening and no one is talking, the universe will be a whirlwind forever. Someone has to break the ice. Others urge caution. They bring up the dark forest analogy. Imagine a dark forest full of unseen hunters. The smart thing to do is to stay silent. To light a fire to shout is to reveal your location to whatever else is lurking in the trees. We know nothing about what is out there. Why would we attract attention? What if a civilization like our own human history shows is predatory? Why ring the dinner bell? This question, should we shout, is one of the most serious we can ask as a species, and we have no consensus. This great silence, as it is called, loops us right back to the Fermi paradox. Why haven't we heard anything? Perhaps our reasoning is all wrong. Perhaps advanced civilizations don't use loud radio waves. Maybe it's a primitive, messy way to communicate. Maybe they use lasers, which we have only just begun to search for. Maybe they use a form of communication based on quantum entanglement or something. We can't even dream of something that looks to us like pure magic. Maybe a civilization, as it gets older, gets quieter. They become more efficient. They stop wasting energy by broadcasting it out into space, and instead they keep it all for themselves. Or maybe they become invisible on purpose. Maybe the dark forest is real, and the oldest, wisest civilizations know that the only way to survive is to be silent. The silence we are hearing then might not be an absence of life. It might just be an absence of loud life, or an absence of life that wants to be found. The search continues. The great quiet listening goes on. We are still here by the shore of this vast cosmic ocean, with our ear to the shell, straining to hear a sound that sounds like home. Here we are, at the end of our long journey. We have travelled so very far, not just across space but across time and thought. We began with a question that has echoed in human hearts for as long as we have looked at the night sky. Are we alone? For millennia that question was the domain of priests, philosophers and poets. It was a matter of faith or logic or pure imagination. But in the past few moments of cosmic time, something changed. We, this curious species on a small rocky world, developed a new way of knowing. We began to build eyes of glass and metal extensions of our own senses that could see farther and clearer than we ever dreamed. We built messengers, robotic emissaries, and sent them on journeys to other worlds. The nature of our quest shifted. It was no longer just speculation, it became a science. We have journeyed from the first precise mathematical understanding of other worlds in our solar system calculations made by pioneers like Kepler to the breathtaking data-rich visions of today. We've seen the universe in new light with the James Webb Space Telescope, a machine that can look back in time and scan the atmospheres of planets orbiting distant stars. We've touched the mist of alien moons flying through the plumes of Enceladus, with the Cassini probe tasting the water of another world. We have gathered so much data. We have found planets everywhere we look. We have found water, We have found the building blocks of life, the same carbon-based molecules that make up our own bodies, scattered like dust among the stars. We have proven that the ingredients for life are not rare, they are common. And yet with every new discovery, with every piece of data, we have not found a simple answer. We have not found the answer. Instead, what we have found is something almost more profound, a universe of unbelievable complexity and variety. For every answer, we find a dozen new questions blossom. We thought life needed sunlight. We found it thriving in total darkness at the bottom of our ocean seams, feeding on the chemical heat of the Earth itself. We thought life needed a narrow band of temperatures. We found tiny resilient creatures that can survive being frozen in ice or boiled in hot springs. This is the great humility of our science. Every time we draw a line and say life must look like this, the universe shows us we are thinking too small. The cosmos is far more creative, more strange and more wondrous than our limited imaginations can easily grasp. The search does not just teach us about the universe. It teaches us about the limits of our own understanding. It forces us to be humble, too. And this brings us to the final quiet truth of our journey. This entire quest, this great, expensive, difficult search for life out there is not perhaps just about them. It is about us. The question, are we alone, is a mirror, a great cosmic mirror. And when we gaze into it, we see our own reflection. We see our own curiosity. We see that deep, unshakable need to understand, to explore, to know what is over the next hill or the next ocean or the next star. It is perhaps the most noble part of our nature. We see our own fragility. When we look at the sterile, irradiated surface of Mars or the crushing toxic atmosphere of Venus, we are looking at alternative fates for our own world. It is a powerful, unspoken reminder of how precious, how thin and how delicate our own blue and white oasis truly is. The search for life elsewhere makes us value the life that is right here, and we see our own future. When we search for other civilizations, we are also searching for a kind of hope. We are looking for proof that a species can become intelligent and technological and survive, that they can overcome the same challenges we are just beginning to face, the challenges of managing a planet, of managing their own worst impulses. Finding them would be finding a new context for our own existence. Whether the final answer to our question is yes or no, it will change humanity forever. If after all our searching we find nothing, if we scour the galaxy and all we hear is silence, what would that mean? It would mean that the spark of life that ignited here is vanishingly impossibly rare. It would mean that all the art, the music, the love, the conflict, the consciousness of Earth is the only consciousness in this dark ocean. It would place a great and heavy responsibility upon us. We would be the sole guardians of meaning, the only voice the universe has. And if the answer is yes, if we one day point our telescopes at a small pale dot and find the unmistakable signature of biology or technology, it would mean that life is not a miracle but a natural common outcome of cosmic evolution. It would mean the universe is teeming with stories with different solutions to the problem of existence. We would no longer be the center of the story but just one voice in a great cosmic choir. We would at long last find our true place in the universe. Either answer is profound, either answer changes everything. Perhaps the point of the question is not the final answer. Perhaps the point is the journey itself. The universe as we have seen is a story. It is a story of rising emergent complexity. It began as a simple hot dense point. It cooled. It formed atoms. Those atoms gathered into stars. Those stars forged heavier elements in their hearts and scattered them into space. Those elements clumped together to form planets. And on at least one of those planets, that complex chemistry crossed a threshold. It organized itself, it began to store information, it began to replicate. It became life. And that life over billions of years grew more complex, more aware, until on a savanna in Africa, a part of that life stood up and looked at the stars and wondered. We are not separate from the universe, we are not aliens to it, we are it. We are the cosmos evolved to the point where it can begin to understand itself. We are the universe's way of thinking. We are the universe observing itself.